Okay? So, there was something left that I should have from yesterday's lecture that I was supposed to tell you yesterday, and I didn't. Well, the first is now a remark added to. So the remark was, let me see. Maybe for these remarks I will start. No, wrong. Okay, so the remark concerns the definition of rectifiable sets. As Tatiana pointed out yesterday, the definition that I and Yoshi gave was based on covering with surfaces of class C1, while she said you can as well cover with Lipschitz images. That in principle would give you a larger class of rectifiable sets, but it doesn't. Okay, and the argument is essentially related to this losing property of Lipschitz map. They agree with C1 maps on large sets. Okay, and there are some details to be fixed. Now, but there is one important thing I wanted to add, is that while the definition I and Yoshi are is particularly convenient to prove certain things, and I will show it in a minute, when you prove the existence of the tangent, approximate tangent space, the other one is more flexible, exactly because it has Lipschitz images. For instance, you can give the definition of a rectifiable set in any metric space, because what is a Lipschitz image of Rn in a metric space is very clear, while what is a C1 surface in a metric space is not clear at all. Secondly, if you want to prove that Lipschitz images of rectifiable sets are rectifiable sets, that's obvious if you take her definition. It's not obvious at all if you take our definition, okay? So the fact that the two definitions are equivalent is actually used in many technical steps if you really work on this stuff. So it's not really that you choose which one. You have to keep in mind both, because one is flexible and the other is better for certain proofs. Okay, so then what I wanted to also to do yesterday, and I didn't, was this definition of proving the existence of approximate tangent space. So let me go back first to the definition of, okay, of what is the usual tangent space, let's say to a surface. Okay, so you have a set E, which now will be a surface if you want. And you fix a point, I think it was called A in yesterday's lecture, and it will stay A. And then what you do, you blow it up around A and looks what happens at the limit. So what do you do? Essentially, if this is the ball of radius r centered at A, you enlarge it and translate so that center becomes 0 and the radius become 1. And then you do the same with the set. So you take this set, this is making the point A to becomes the origin, and this is the enlarging factor. Okay? And what you get is that this becomes the ball of radius 1 centered at 0. Okay? And the set ER is this. And of course, now if E is a surface, of class C1, then what you have is that this set here, this blow up, looks more and more like the tangent plane. Okay? closer and closer to the tangent plane of E at A as r gets to 0. Now, if you want to be precise, well, it doesn't get uniformly close, okay? It gets closer and closer on any fixed ball. So what you have is the following, that whenever you intersect with a fixed ball of centered in 0, then in Hausdorff distance, this closed set will converge to the tangent plane intersected this. And this convergence is in Hausdorff distance of closed sets. Well, actually, of course, this happens as long as that's not a boundary point of the surface, because if it's a boundary point, you will converge to half of this plane, right? Okay, so actually, if you look at certain maybe old-fashioned books in geometry, you will get that there is a definition of tangent space to any set, which is based on this idea. You blow up and you ask convergence. Okay, so now we want to define tangent space to a rectifiable set. Clearly, you can't expect this to hold. Okay, and the reason why this is not holding, okay, I mean, if you take the simple example, the nice example of rectifiable set, this holds, okay? Because if this is your rectifiable set, of course you will have trouble in this point, you will have trouble in this point here, but essentially in all other points you have this convergence. But this is not the case in general with rectifiable sets, okay? This is because this is a particularly nice rectifiable set. The bad example of rectifiable sets you have to keep in mind is the one I suggested. You take a dense family of points, and from each one of these you take segments going out in a dense family of directions, and the only requirement you have to put is that the sum of the length of all these segments is finite, but then you get a set which is dense everywhere. And clearly these things, when you do this kind of operation, will not converge to a plane, okay? Because, I mean, it will converge. In fact, if you do something like this, whatever is, but in the end you get Rn, you fill everything by blowing up at a point, because you have points everywhere, okay? So this doesn't fit, this notion of tangency doesn't fit rectifiable sets, which of course was already told several times. By now you know that very well. So what is it that it does? Well, the idea is that instead of looking at sets, you look at measures. So you don't require, in the definition of approximate tangent plane, you don't require that these sets converge to this plane, but you require rather that the the d-dimensional measure Hausdorff measure restricted to the sets converge to the d-dimensional measures restricted to D. This makes all the difference. Okay, so you don't look at sets anymore. You look at measures. So the definition is the following. So let E. Okay, let me be sure I don't forget. Okay, let E be a set in Rn. Now I don't require it to be rectifiable, but it will come in a second. I will just give a definition of tangent plane with which is HD locally finite. I mean that the measure is HD is locally finite. Then let E to A to be a point in the set. Well, actually, it's not important for the definition. And And then we say, and let T be a plane, a D plane. Okay? Then T is the approximate tangent plane to the set E at A. If the following holds, well, as I said, instead of looking at, you still look at this, instead of looking at these sets, you look at the corresponding measure. So if HD restricted to this converge weakly in the sense of measure to HD restricted to T, okay, as R goes to 0. And maybe we want to call this, we will use it later, call it mu AR here, and maybe we put E here. And this we might want to call mu T. So now in the following, mu T is simply short for restriction of the Hausdorff measure to the set T. Okay, so no. Well, here comes the point. I would allow that if I were not able to prove that there exists a unique one. Now, what happens is, next is the theorem, for a rectifiable set, you can prove that such a tangent plane exists, and so you're happy with this definition, because that's a more complicated story. Depends on the purpose you have. Now we want only to talk about rectifiable sets. We can prove something very strong. So why weaken the notion of tangency, right? But of course, if you start from something which you are not able to prove easily that there is a tangent. Okay, so if you start from a measure and you want to define, then you have to do something more complicated, like yesterday, and look at all possible limits you can get. In some sense, this definition is tailored on the results I'm going to say now. And so it's simply because we have these results. Otherwise, of course, we would have to think about something more complicated. Okay, and the result is the following. If E is rectifiable, then the tangent, the approximate tangent plane, which I denote being unique, I denote this way, exists at HD almost every A. Is it? Well, yeah. No, right, that's essential. Thanks. Okay, so this is what I'm going to prove, and that, okay, somehow these are the details about things in some sense have been already used through these lectures. So this is a basic result. Okay, now let me see what is the lemma behind this. This is a theorem, but the lemma which really proves it is the following. If E as above and M is a C1 surface, d-dimensional C1 surface, then at the points of E which lies in M, the tangent plane, the approximate tangent plane to E will be exactly the tangent plane to M. So the tangent plane to M at A, which exists as the classical one, agrees, so is approximately tangent to E at A for not every A in the intersection, but almost every. Now, if you have this lemma, you're done. Because now this proves that for almost every point in this intersection, the tangent plane exists. Well, that's what it says. And since you can cover a rectifiable sets by countably many surfaces, almost all of it, well, then you're finished. You also proved the theorem, right? Okay, I mean, the argument now, I'm going to prove this lemma only. The argument doesn't require at all that E is not rectifiable. The truth is that if E is not rectifiable, this intersection will be negligible and the statement is empty. Okay, so it doesn't require that, but it's not particularly interesting when E is not rectifiable. Okay. Sorry, if it's purely unrectifiable, I should have been more precise. Okay, so this lemma doesn't use much, and okay, it might look a bit complicated, but in fact, this lemma is just a consequence of Radon-Nikodym theorem. Okay. Okay, so what we do is we write the set E as M minus the part of M which is not in E, which we call F. And then we have to add the part of E which is not in M, which we call G. Okay? So what happened to, well, of course, then this decomposition carries over to the blow up for obvious reason. And it carries over to the measures, because all this, so what you get is that this mu xr e, so these are the measure you are interested in, you can write as the measure associated to M minus the measure associated to F plus the measure associated to G. Okay? And now my claim is that, to conclude, we must show what? That we show this, that if the first addendum there converge to the tangent, to the measure on the tangent, sorry, it's X, but it should have been A. I knew that this would happen, but never change notation. Okay, so this is converged to this, where T is the tangent to M at A, and this happens for every A. Okay, and this is sometimes due to the fact, okay, we are in the smooth setting. I hope you believe that once you blow up your surface, then the measure on it will converge to the measure on the tangent, because in some sense you have much better convergence, okay? So this I take for granted as obvious. And then what I have to show is that these two other things go to 0. As R goes to 0 as always, But this only happens for almost every A. Okay, and this is it. If I have this, I'm finished. I said this is obvious. Let's check this. Okay. To prove this, maybe it's a little bit more convenient. I mean, these are two positive measures, right? I want to show that they converge to 0. Let's just prove that the sum converges to 0. So define this as the sum. About what is it? Okay, then this is just the blow up of the measure lambda. It's just the measure mu xr associated to the set which is what is it? So the union of these two sets, which is the symmetric difference of M and D. Okay, so it's just the symmetric difference of M and E. You take the measure on it, the restriction of the d-dimensional Hausdorff measure, and then you do this blow-up operation. Okay, so by the way, I'm somehow cheating a little bit with notation. I start to define the blow-up for the sets in a nice geometric way, and then somehow I'm using the notation in such a way that the blow-up for measures introduced yesterday is somehow is the same notation, but in fact it is true. Somehow when I blow up the sets and I take the measure on that, it's like blowing up the measure. Okay, so I'm not precise about that because there is no contradiction. There is. Okay, so I want to prove that this goes to 0. Okay, and what I prove, let me do it in the right order. Okay, yes. Let me see what happens to this, to the mass contained. So, I mean, how do you prove that a sequence of measure goes to 0? Well, for instance, you can show that every ball, the mass goes to 0. That's it. Okay? Let's start with the ball of radius 1, centered in. Okay? So, I want to show that this goes to 0. In fact, I want to show it for every ball of radius r. I show it for the ball of radius 1 because it's somehow simpler with notation, but in fact, I mean, it works for every ball of radius r. So if I show that the mass disappears from the ball of radius r, of course the limit will be 0. Okay? So I want to show that this goes to 0. But what is this? Well, this is the measure. Now let me, I take the non-scaled measure, the mass of the original measure contained in the ball of center A and radius r divided by r to the d. This is exactly how what it is, okay? Which is, so and by the way, if you want, this is h d of this symmetric difference okay? But let me write in a slightly different way. I'm saying that this is up to a constant asymptotically equivalent to this divided by mu m. Okay, what is this? I mean, this is the amount of mass of area of the surface M in a ball centered at A and radius r. So this goes like r to the d, okay, because that's a smooth surface. R to the d times a constant, okay, which is the unit, the measure of the unit ball in Rd, which I don't put here, so this is not asymptotic equivalence, it's asymptotic equivalence up to a constant. But I want to show this goes to 0, okay, so. And now if I look at this, I say, well, okay, but I know what the limit of this is. This is Radon-Nikodym theorem. The limit of this is the density of this measure with respect to this measure. Yeah, that's all this was made in order to go to Radon-Nikodym theorem. So this number, as r goes to 0, converge to the Radon-Nikodym density of lambda with respect to mu m at the point A. Density. Okay, and this is Radon-Nikodym theorem. But then I said, okay, what is? And this is true not for all A, but for almost all A. Okay, and now I would like to show that this is 0. So what I wanted to show is that this goes to 0, right? I want to show this goes to 0, so I only have to show that this is 0 for almost all points in E intersected M. Well, why so? Because this density, you're right, okay. Where is it? That I wrote it. Where is lambda? Oh, yeah, here it is. Okay, so lambda is the Hausdorff measure, d-dimensional Hausdorff measure restricted to this set. So its density, it is, if you want, its density with respect to the Hausdorff measures on M is just the characteristic function of this set. And this is 0 in the point of E. Okay? So in particular, I get 0. And so what I've proved is that this goes to 0. So the amount of mass of this measure inside the ball of radius 1 goes to 0, so the limit will be 0 in the ball. And the proof, in fact, doesn't depend really on the fact that here I have the ball of radius 1. I just made it for convenience so that here I get the ball of radius small r. But if I had here the ball of radius big R, here I would get and so on and so on. But the limit is still that one. Okay? So, end of the proof. And it was just to say, I wanted to somehow to tell this proof to show that some of the statement may look a bit non-obvious if you look at pictures of complicated sets, but in the end relies on something very general like Radon-Nikodym theorem. So in some sense they are very soft kind of statement. Okay? There is nothing deep in these things. Let me add a corollary about this. So I've proved that the tangent space exists for a rectifiable set. Here? Yeah. Because if you want to write this measure and you want to start from this measure, okay, right. Okay, so this measure. So you want to compare this measure and this one. Right? I mean, so this measure is not absolutely continuous with respect to this because there is a piece, A minus M, which is outside. Okay, but the restriction of this measure to A minus M will give you the singular part of this measure with respect to this. But the singular part has density 0. The absolutely continuous part of this measure with respect to this will be simply HD restricted to m minus e. So what will be the characteristic function of m minus e? So what is the density of this restriction? I mean, so you obtain, so this will be the singular part of the measure. This is singular with respect to this. So this is the singular part of lambda, and that's density 0, being singular. And the absolutely continuous part will be this. And how I obtain this measure from this? By multiplying by the characteristic function of m minus e. Right? I just have to take away the part which is in e. So this measure and this measure, I obtain this measure by multiplying this measure here by the characteristic function of m minus e. And the characteristic function of m minus e, okay, this one if you want, or it's the same from the viewpoint of density. This is 0 in e. So this is, I'm using the fact that radon-Nikodym density is the one you take when you represent a measure as a function times another measure, but it agrees with the limit of the density. So I'm simply using, this is radon-Nikodym theorem, tell us that whatever function you use to represent a measure with respect to another, then this ratio will converge to this almost everywhere.
So the singular part doesn't come out of radon-Nikodym derivative?
In radon-Nikodym derivative, this, okay, if I take a measure singular with respect to another one, radon-Nikodym derivative will be 0.
Almost everywhere.
Yes.
And that equality was also almost everywhere.
This is, yes, it is here. Yes, almost everywhere. Okay, these are measure theoretic details, okay, so I think that I got them right, but I'm going very fast on this because. Okay, so let me give you some corollary of this and remark. Okay, the first one, which is, there is something maybe not completely obvious about this definition, because the way the tangent space to a rectifiable set is defined is intrinsic, doesn't depend on what I use to cover it. So the lemma says, well, using this lemma, whatever cover we choose of E with surfaces, I will get a tangent bundle, if you want. But in the end, the tangent space is intrinsic, so it shouldn't depend on the cover. So if one thinks about this, then means that somewhere in this proof, we have shown the following. So implicit in the proof is that if you take two surfaces of class C1, they have the same tangent almost everywhere in the intersection. It must be there, right? I mean, otherwise it cannot work. So that the tangent to M at A and the tangent to another surface M prime at A is the same for HD almost every A in the intersection. Otherwise, there would be something strange in this construction. This happens to be true, and just if you have time to figure out, okay, this we're talking about smooth surfaces. That should be a lemma that one is able to prove without radon-Nikodym, without big theories, right? So just, it is true. Sorry, where? Two rectifiable sets. Yeah. Let's say the problem is that they might not have a tangent. But if they do, yes, they are the same. So let's say you take two rectifiable sets. Okay, so this is true. Yes. Okay, you can prove, yes. Yes. Okay, you can, Yes. So let's say you know this tangent. Okay, so let's say that this is a rectifiable set, or you know that this has tangent plane at almost every point. I will come to this in a second. Okay, then this other set will have, I mean, it's the same proof, will have a tangent plane at that point for almost every point in the intersection. So this works in general. I'm simply pointing out that at least for surfaces, one should be able to prove this because it's a classical statement, right? But it's true, this identity is true for every, so the tangent bundle, so to speak, is local. Okay, if two sets agree, I mean, in the intersection of two sets, you have the same tangent bundle, almost everywhere. Right, yes, of course. Okay, this is one remark. The second one is that from this definition of tangent space, we get something about what happens, something a bit more, if you want, concrete to look at. So far we spoke about convergence of measures. Let's give something more precise, okay? So I have my rectifiables, my set E, not necessarily rectifiable, so it's sort of a mess, but there is a point where it has an approximate where it has an approximate tangent. So assume it exists, the tangent plane at a point. Okay? Now I look what happens in a ball of radius r. And what I would expect from some notion of tangency in some sense is that, well, most of E should be close to the tangent plane, and very little should be outside, right? So let's make this precise to have something. So I take the cone, I fix an angle alpha, and I take the cone centered at A with axis T, okay, and angle alpha. So this cone is the set of, to be precise, a set of points A plus H, such that the distance of H from T is less than sine alpha times H. Okay? So I take this cone here, and what I expect somehow, I would like to point out, is that somehow I expect that most of the set E should be inside the cone and very little outside. Okay? So I have here. Okay, and so then, in fact, starting from that definition, you can prove easily. So this is no hard theorem, but it's that first you look at what happens to the measure of the set, which is not in the cone. Okay, so you look inside the ball. Okay, you look at what is in the ball, because of course the statement will depend on R. You look at how much of the set which is in the ball is outside of the cone. Okay, you measure it, so you're looking at these little pieces here. Remember the bad rectifiable sets. There will be always little pieces of the set around here, okay? Because the support of that, of the measure of the set, I mean, that set is everywhere, okay? So there will be stuff here, but what I'm saying is that what the theorem above says is that the amount of stuff of measure here outside of the cone gets smaller and smaller as R goes to 0. In particular, this is small o of R to the D, while the amount of measure you have inside the cone is not small o of R to the D. In fact, it behaves as it should be, like the amount of area of the plane inside the ball. So you have these other things. This is asymptotically equivalent to r to the d, well, times the area. So you want the area of the disk, the d-dimensional volume of the disk of radius r. So here you take alpha d, where this is the volume of the unit ball in Rd. Okay? But let me point out that the theorem there, the definition is even more precise because it's telling you exactly how all this mass is distributing. It's not just that inside the cone you have this amount. So for instance, as long as you have this, these two statements are compatible with this situation. Two sheets that get here in one point, then of course if you look at the amount of mass inside the cone, you get exactly these holds, but in some sense this is wrong, right? I mean, all the mass is on one side and nothing on the other. What is written up there is much more precise. It tells, oh, this is not the generic picture. So these are corollaries of the previous statement, but are way stronger because tell you exactly where this mass is going to be distributed. So maybe this is geometrically more intuitive, but the powerful definition is the one above. However, let me keep this for the last remark. And the last remark is, I think, what makes the theory of rectifiables, one of the remarks that makes the theory of rectifiable sets nice, the definition nice, and is the following. So we proved that rectifiable sets have a tangent plane. Well, what about the vice versa? We said we can define tangent planes for every set which is HD locally finite. Is it the vice versa true? Let's say that we have this tangent plane exists at almost every point. Well, then it's the nice part of it is then the set is rectifiable. So this is the existence of tangent plane is a characterization of rectifiable sets. Okay, and somehow this is I think it's implicit in what Tatiana was saying, and this is in the proof. You always but let me add this. So the vice versa is true. So if E is, okay, please mind you, if it is as locally finite measure, okay, has tangent plane approximate at HD almost every point, then E is rectifiable. In fact, it's much nicer than that. You don't need the existence of tangent plane in this very strong sense. This is enough. In fact, it's enough even with a fixed alpha, so the existence of an approximate tangent cone. Meaning, what is a tangent cone is a cone such that there is very little of the set outside. Okay, this holds. Indeed, it suffices that star holds, not for all alpha, just for one. Well, maybe not pi over 2. For some alpha. Alpha less than pi over 2. And for almost HD, almost every A in E. Okay? And the alpha may depend on the point, if you like, because that's not. So, I mean, one thing, you might think, okay, this looks like a hard theorem. It's not. These kind of theorems are easy compared to the theorem that Tatiana has been mentioning so far. So all the theorems she mentioned in her lectures are much harder than this. This is, in some sense, a relatively easy theorem to prove. Okay? I will not give a proof of this, but I will, at some moment, tomorrow, I will show I will prove at least one rectifiability result. So No, because if it's not positive, do I? Okay, let me check. Do I have to ask?
You need a lower bound on the density, but here you have, your set has positive, and your set has positive and finite H measure, which is called an H.
Yes.
Almost everywhere, your lower density is bounded by a number, and that's the measure he's using H is the H. Almost
Yeah. It's
everywhere.
sorry. Is it? It's written. I think.
So you have a little
No, I need that the upper bound is finite almost everywhere. That I have for granted. The lower bound of the lower density can be 0 for some sets, but they are.
by almost every, but not almost every.
Well, in the end, it will not because they are rectifiable. Okay, wait. Let's say. This means I might want to check whether there is an additional assumption. So I don't want to. You might be right. Okay. My memory was that there is no additional assumptions, but
What happened is in your definition when you wrote that definition there,
yeah.
where with convergence, somehow hidden in there, you have that the density is 1.
Yeah, but that's not the claim. I'm claiming that I use only this one. That's why he was asking. Because, of course, yeah, sure. In that definition, it's required that the lower density is. No, I'm saying that. Maybe. Yeah, I think so. Okay. Yeah, you're right, I think. Okay, so for this is correct because it's implicit on the existence of the tangent plane that the density will exist. Okay, of that definition. What is here, you need something more. Sorry. And that the density, the lower bound on the density is positive, okay? Because otherwise, yes, the proof fails, I agree. Okay, but this was, so this was simply to say that you need less than this, okay? Tomorrow I will show one rectifiability results and the kind of idea, which is a elementary one compared to the other mentioned in this course, but the kind of idea which is behind that proof can be used more or less in this setting. So I will not prove it for this, I will prove it for finite perimeter sets, but it's the same type of argument, okay? So it's one of the few elementary arguments in rectifiability, that you prove a rectifiability in a relatively easy way. All the rest, sorry, I think it's awfully complicated. Maybe you don't agree, maybe it's easy.
No, sorry that you're biased. You think that that's the easy one, that's the one that you know well and work with.
No, that's the one I learned when I was young. That's how it works. That's the easy part, right? Whatever you learn after you're 30 years old is no longer easy. Finally, finite perimeter sets. Okay, so let me recall what is the goal here, why people started defining this object. The point is we want to generalize the notion, we want to generalize the notion of a domain with smooth boundary in Rn. Okay, and so when we think about, what would be the generalized surfaces will be the boundary of this generalized domain. Okay, so we are implicitly thinking of defining surfaces. Not just surfaces in a generalized sense, but surfaces which are boundaries. Okay, so that's why this theory, in some sense, only produce surfaces of codimension 1. Okay, so this notion generalizes the notion of domain of sets with smooth boundary. In Rn. Okay, and when I say generalize, keep in mind that in some sense I want to apply this, people wanted to apply this to prove existence results, so the things they care most was that this generalization should give you easy compactness results. So in some sense, the definition is designed in such a way that compactness in this new class of sets is somehow easy, because that's the purpose of it. Okay? And okay, so let's begin with the remark. And the remark, which is the starting point of all this, I mean, at least it would be the starting point nowadays, not when these things was imagined, would be, okay, let's say that we have a set with a smooth boundary. But let's say closed. It's not that important. Smooth boundary. Okay, smooth actually here means C1. We will see it in a second. And then I ask this question, okay, what is the distributional gradient of its characteristic function? Okay, and here, as I said, this theory, like the theory of currents, is somehow implicitly based on the notion of distribution and distributional gradients and so on. Okay, so, well, let's do the computation. How do I define the distributional gradient of a function or of a distribution for that matters? So the definition of this is, okay, I define, first of all, I define what is the action on a test. Okay, what should be the test? Well, the gradient would be a vector valued, it's a vector field, right? It's a vector valued map. So it acts on vector, to produce a number, it has to be integrated against another vector valued function. Okay, so the test will be vector valued vector fields. Smooth, because that's in the theory of distribution, compactly supported as well, and then Rn. Again, because I'm defining a vector distribution, it has to act on vectors, okay, on vector test function. And what is it? Well, okay, now you may not know the theory of distribution, but you know how it works. You should do implicitly a change of integration by parts, and you say, well, okay, this is minus the action of the original function, that's the definition actually, minus the action of the definition on the divergence of phi. Okay? That's what it should be, right? This, which is, well, in this case is just minus the integral over E of the divergence of phi. With respect, I mean, this is really Lebesgue measure, okay? Because this sets. Okay, and now you say, well, but now this set has smooth boundary, so I know what to do with this. I can apply the divergence theorem. So by the divergence theorem, this is equal to minus the flux of this vector field through the surface, through the boundary. Okay, and here I integrate over the boundary, where this is the outer normal to my smooth surface. I mean, my set with regular boundary. Okay, and now I just play a little trick for convenience. I say, well, let's take that to be the inner normal, well, which is not in the usual divergence theorem. Okay, in the divergence theorem, usually it's the outer normal. So this will be the inner normal. Okay, but then if I look at this, I have this abstract linear functional, which is called the derivative. But if I look at this, I say, well, then I have a representation. It is a measure. I'm integrating here phi against a vector measure, right? So I guess that is the distributional derivative. What is the vector measure is hn minus 1 restricted to the boundary and multiplied. Okay, of course, it's a gradient, has to be a vector. What is, okay, this is a positive measure. I get a vector measure by multiplying by a density vector function. What's the density vector function? It's exactly this one. Okay? So this is a positive measure. This is the orientation, so to speak. Okay, that's it. But then one says exactly in the same way you define, if you want, derivative of Sobolev function or even the curvature, mean curvature of a varifold, you start from a formula which is true for smooth objects, and then you say, okay, if my object is not smooth, such a thing does not exist, but I can define weakly this measure simply by, I take this as a definition of the derivative, okay? So that's exactly, now you say the following. So this is the definition. Let me get it precise, maybe. A set E in Rn has finite perimeter if its distributional derivative is represented by a vector measure. Is represented by some vector measure Okay, how do I write vector measure? I like the idea of writing them as a positive measure times a unit density. Okay. So measure a positive finite Borel measure. So nice positive measure. And this eta will be a unit vector field. So I can always represent vector measure like this by Radon-Nikodym theorem if you want. So I will stick to this. Okay, so that's the definition of finite perimeter sets. Let me translate this condition. So we can forget about this. Let me translate this into a formula. Okay, just to recall, the formula is the following. That if I integrate, well, it's what's written there, the divergence of phi over E, I get, with respect to Lebesgue measure, okay, let's put it here. Then I get, is the same as integrating phi scalar product eta with respect to d mu. Okay? For every test function, smooth, test vector field, smooth and compactly supported. Okay? Well, now this is standard function analysis, right? If this is a measure, you can pass from smooth, compactly supported vector field to all vector field which are C1 and goes to 0 at infinity. Okay, that's standard function analysis. Okay, but so I will not always stick to smooth and compactly supported. I can enlarge the class for which the identity is true once I have it. Yeah. Otherwise, it's nice, positive, finite. Sorry, let's make it finite. Sure. Otherwise, I would call the set, if it is locally finite, I would say that the set has locally finite perimeter. Okay. There is one point I would like to underline. In this definition, one might tempted to say, well, did I ask anything about mu? Maybe I would like to ask that mu is h n minus 1 restricted to a nice set. One would like to put it there, right, to make it more similar to the formula I gave before, to this one. But it's not in the definition. That's a theorem, okay? So the definition, without requiring anything on mu, we will see it will give us compactness almost for free. But then there is a price to pay. Then you have to prove, and it's a theorem which is not completely trivial, you have to prove that this is actually the measure on a the restriction of hn minus 1 to a rectifiable set. So that's a theorem, is not in the definition. And the reason is that with this definition, compactness comes for free, but then, of course, you have to show that this is a nice measure, okay? So that's the rectifiability theorem, and this somehow the most important part of the theory, if you want. So a very quick historical note. The definition in this sense, well, in a different language, but it was meaning this, was given by Cacciopoli. When the paper came out, the reviews of mathematical reviews was done by L.C. Young, who criticized very strongly the definition, because he said, well, this guy is claiming that he can prove the divergence theorem in every surface, define everything, and it's bullshit, because this is a purely formal definition. I mean, in some sense here, the divergence theorem is not even a theorem, it's a definition, right? I mean, what is this? Okay, then later, and that's exactly, I think, in some sense, because this measure mu is not special. But then later, 10 years later, De Giorgi proved that this measure is a good one. It really leaves, it's the restriction of hn minus 1 to a rectifiable set, showing that this is, and then there is the review of L.C. Young again to that paper, saying, well, maybe the original definition was not that bad. But this is the point, right? I mean, if you do things too absurdly, you are subject to criticism, and quite correctly. So nowadays, I mean, we might consider this a right definition because we got used to it. But when it came out first, it was criticized for a good reason. Only when De Giorgi proved that this is not such a strange measure, people were convinced, okay, this is not cheating by constructing some absurd space. Okay? I mean, you can define Sobolev spaces by completion, but you get an absurd metric space, right? And then proving the existence of a solution of a PDE in an absurd Banach space, it's not clear what it means. You have to know that Sobolev functions and are differentiable in some sense. Otherwise, what are you proving? Okay, so that was the criticism of the original definition. And it was solved somehow when De Giorgi proved that these measures are not too bad. Okay, that's the historical note. So here are some remarks. And the remarks, the first is, well, when is it that we have such a measure? Can we translate it into something more manageable? So the question is, okay, so the definition is, if the distributional derivative is a measure, then that's a finite perimeter set. Okay, when does it happen? Can we translate it into something more concrete? Okay, so here is the first remark. So the question amounts to say, when is the functional, the linear functional, that takes every test vector field phi into this integral, when is this, well, this is always defined for phi. Okay, when is it represented by a measure? Okay, answer, this is functional analysis when it is bounded with as a linear functional with respect to the, what is it? Not the uniform norm, it's the supremum norm, okay? So the answer is that, the answer is when it is bounded with respect to supremum norm. Because it's the usual game, Riesz representation theorem. Okay? Every functional and continuous function endowed with the supremum norm, which is bounded, is represented by a measure. Okay, so but what does that mean? Well, it means that if I take the supremum of these things over all vector fields in the class, which are less or equal than 1 in supremum norm, well, let's put it like this, so we have no doubt, then this is finite. Okay, that's how you show what it means that it's bounded as an operator, as a, sorry, a linear function. Okay, and now there is a name for this. So when is a set of finite perimeter? When this inequality holds. And then you give a name to this. This object is called perimeter of E, and written in short, P of E. Well, it has a geometric meaning, of course, and the geometric meaning is the following. Well, what is this? It's just by definition, okay, no, by Riesz representation theorem, this is the norm of this linear functional, but it agrees with the norm of the measure which represents the linear functional, okay? Because that's what Riesz theorem says, that the representation is in isometry, okay? So what we have is that P of E is equal to the norm, let's say the mass, of the vector measure which represents the boundary, okay, the derivative. Okay, but this is a unit vector, so the mass of this is just the mass of mu. And what is the mass of mu? Total variation, call it as you like. Well, in case E is a smooth set, we said that mu was just Hn minus 1 restricted to the boundary. So at least in the smooth case, so now last equality only works when E is smooth. We said that this measure mu, I mean that's what we wrote before, and it's no longer here. It's this measure mu is just Hn minus 1 restricted to the boundary of E. So what is that? Is the measure of the boundary of E. So that's why it's called perimeter, okay? Because it extends what would the perimeter should be, okay? So actually, this identity for the time being only works if E is smooth. Then somehow part of the theory is showing that in some sense this can be holds also for an arbitrary finite perimeter set, okay? Pop, pop. Okay. Examples of finite perimeter sets. Now, I will keep the one above. So examples, and this probably will be it for today. Okay, there are many easy examples. but there are also bad ones. And keep in mind, you cannot only rely on the nice examples, right? Because then you get some vague but not precise impression about what this you're talking about. So examples. Well, sets with smooth boundary, that's what we already said. Sets. So E with smooth boundary, maybe finite mass. Okay, so if it is bounded, yes, and otherwise finite area. That certainly, it's somehow we started from that, right? Okay, there is a second example. Okay, this is a distributional definition, right? So imagine that you take E and you add a set of measure 0 according to Lebesgue, or you take away a set of measure 0 according to Lebesgue. Then, on the left-hand side over there, nothing changes because you are integrating over E with respect to Lebesgue measure, so nothing changes. What does it mean? It means that if you modify E in a set of Lebesgue measure 0 by adding or subtracting, it will still remain a set of finite perimeter with the same derivative as before. Okay? Okay, well, in short, I mean, you can always perturb a set of finite perimeters in a set of measure 0, nothing changes. Because in the definition, which is distributional, you integrate with respect to Lebesgue measure, and the rest doesn't. Okay, this is telling you that there are many examples of bad finite perimeter sets, which are not that bad after all, because let's say you start from the disk. This is a finite perimeter set, and then you add this, and then maybe you take away this. It is the same finite perimeter set as before, in short. Okay, so you have added this, you have taken away this, so you have changed the topological boundary of the set, but you didn't change the distributional derivative of its characteristic function. So in some sense, of course, then you can make a mess out of it by adding a countable dense set. Okay, you change completely the topological boundary, but it's not really an issue because you say yes, but we started by something very regular, very smooth, and we just mess it up by adding a set. Okay, so keep in mind that you can always mess things up by adding a null set, in particular a dense countable set. So this means that the connection between distributional derivative of the characteristic function and boundary, topological boundary, is not that good because the first is invariant with respect to this operation, the second one is not. Okay? But so far, in some sense, one says, well, okay, this is the same as this. In fact, if you want to be precise, people would say that finite perimeter sets are equivalence classes. Okay, we don't take that line, but we keep it in mind. So we distinguish sets, but keep in mind that somehow they should be treated as LP function, equivalence classes, not exactly as function. Okay? Very well, so this is not really okay, other sets which are here, well, piecewise smooth, or even Lipschitz boundary. Where Lipschitz boundary means that the boundary can be locally written as the graph of a Lipschitz function. Okay? They are fine. Okay, now let's say I ask you to prove this. What you would have to do is to show that the divergence theorem works also for these sets with the Lipschitz boundary, and that's not the standard version of divergence theorem. I mean, the one that you learn in calculus requires some smoothness, not Lipschitz, but you can prove it. Okay? So to prove that this is a finite perimeter set, you actually have to prove, and you are doing something stronger, prove divergence theorem for these sets. Now, then I ask you as an exercise, think about this. What is the class of, largest class of sets that might be of finite perimeter and that you can define in some sense in a classical way? Okay, like extending the notion of piecewise regular or whatever. Think a little bit what you can come up with. Okay, so what I'm saying here is that you don't need to have a smooth boundary. But okay, so how far you can push this? What is the wildest example you can produce without going back? I mean, of course, you can say a finite perimeter set is such if it is a finite perimeter set. But that's a tautology. I'm asking for something which is not a tautology. Okay, something that you can, some description of possibly classical flavor, which is there. For instance, let me see one thing which is certainly there is the following. Okay, this is not in none of the previous classes because this is not Lipschitz boundary. Here you have a problem. But it is a finite perimeter set. And if you want, the reason is that you can obtain it as limit of two pieces which are nicely irregular and you glue them together. Or if you want, the other argument is that all the troubles comes into a point. But from the viewpoint of distributional derivative in the plane, a point is not relevant. In fact, there is a sort of removability argument which says that if you have a nice distributional derivative in the plane minus a point, well, the same distributional derivatives works also in the plane with the point. So in some sense, one point of mass is not a problem. Presumably, a set which is messy, of messy things, which is H1 null, H1 null is also not a problem. But then now you can start imagining what could be a statement which gives you some class of finite perimeter sets. So I leave it to you. Think about the statement and propose it tomorrow and see whether it's the most general one. Okay, and let me finish very quickly. So the other things you have to keep in mind is that finite perimeter sets are easily closed by finite union and finite intersection. Which make them very flexible in some sense. That's not so easy to prove, but okay, I mean, it requires a little bit of technology, but not much. So you can start taking union of these things that's also a finite perimeter set. Okay, and then so far these are nice examples. They don't exhaust, however, the class. None of these classes exhaust the class of finite perimeter sets. So let me give you a bad example. The bad example is as following. It takes 1 minute and I will be done. Promise to be quick. Take a sequence, dense sequence of points. Take a sequence of radii which are positive, okay, being radii, and such that the sum over I to the n minus 1 is finite. And then you start constructing a set like this. You start construct a sequence of sets. So the first one will be given by the first ball. The second one, well, you take the first set you had, you take the second ball, and you take the symmetric difference. So if this was the first set, the second one could be this. So you add the part which is not inside the previous one, and you take away the part that was inside. And then you keep it going like this. So let's say you get here. I'm trying to draw the worst possible cases. Okay? And now you take E to be the limit of EI as I goes to infinity. What do I mean? I mean that you endow sets with L1 distance. So the distance between two sets is the measure of the symmetric difference, or the L1 distance of the corresponding characteristic functions. And I claim that the limit exists. Limit with respect to L1 distance. It exists because you easily show that this is a Cauchy sequence. And then I claim that this is a finite perimeter set, and that the measure, the positive part of the measure, which gives the derivative, well, see what happens here. Every time the boundary of this object was the boundary of the first ball, then the union of the boundary of the two balls, because the way I constructed the sets, there is no cancellation. So the boundary of this will be the union of the two boundaries, and so on and so forth. So what will be the boundary of the limit set will be the union of all the disk of all the spheres. Okay, and so it is this. The mu in the definition of whatever it's the mu, that mu there is just h n minus 1 restricted to the union of these spheres. Okay. Why this example is bad? Because there is no way, by modifying it in a set of measure 0, to get a nice set. This set is density. Its distributional derivative, I mean, this measure has support Rn. Okay. But it's not that bad after all. It's still a measure supported on a rectifiable set. Okay. And this is as bad they can get. Okay, so the theorem of de Giorgi shows that more or less that's the worst case you can get. Okay, but if you try to imagine something that could be true for finite perimeter sets, always test it on this type of sets. Okay, if it passed this test, probably is true. If it only passed the test with this type of sets, presumably will be false for finite perimeter sets. Okay, so thank you very much, and sorry for the overtime.